Hello everyone, welcome to my class. This is the second of Calculus 3 class. In our last class we covered three-dimensional Cartesian coordinate systems, and in today's class we will start vectors. So let me start the class right away. First let me give you a definition of vectors. A quantity that has both a magnitude and a direction is called a vector. For example, displacement, velocity, acceleration, force, etc. are vector quantity. A vector is denoted by putting an arrow above the letter, lowercase letter. For example, A vector, B vector, C vector, ... or by a boldface letter. That's a boldface A, boldface B, boldface C, etc. Geometrically, a vector is represented by a directed line segment as follows. This is the vector A, which starts from here and in this direction. So this is the directed line segment. Vector B is the vector AB, which starts at A, ends at B. So B is called head or tip or terminal point, and A is called tail of the vector or initial point of the vector. Vectors are free floating directed line segments, so locations do not matter. So in the first diagram here, these are the vectors in 2 dimensions. In the second diagram here, let's say one vector, which is this vector here. Let's say this vector has component 2 and 3. Then this means the tip is 2 units right from the tail and 3 units up. Component wise, we can write the vectors in 2 ways. One is a row wise and one is a column wise. In a row wise, for example, we use angle brackets and separated by commas. So one component is 2, another component is 3. So for example, here we graph there, and column wise we writing vector using bracket here, so 2 and 3. Great. Quick alert: components describes a vector, so locations does not matter, and coordinate describes a point, location is fixed. Some basic definitions. A vector with its tail at origin is called the position vector. So for the point P, the position vector is OP. For example, for point P coordinate 4, 5, its position vector is OP. Then the vector is 4, 5. So position vector and the point. Quick remark: any 2 points in the plane or in the space determines a vector starting from point A ending on another point B. For example, the vector AB starting at A ending at B is x2 minus x1, y2 minus y1. So which is also called tip minus tail. Awesome. Let's move on. The magnitude of vector AB is denoted and defined by the distance formula. So simply the magnitude of AB equals to, under the radical, x2 minus x1 is square, outside is square, plus y2 minus y1, outside is square. In fact, the magnitude of a vector V with component A, B in R2 is simply under the radical A square plus B square. Think V as a positions vector. Similarly, the 0 vector is denoted by the 0 vector has magnitude 0 and no directions. A unit vector is a vector of magnitude 1. So for any non-zero vector V, the unit vector is denoted and defined by V hat, which equals to V over its magnitude. So the total magnitude turned out to be 1. Note, V and its unit vector have the same directions. Note number 2, the process of dividing a vector by its magnitude is called the normalizations of a vector. Great. I know there are lots of definitions. Next, there are 3 special unit vectors along the coordinate axes. One along I is along x-axis, j unit vector along y-axis, k unit vector along z-axis. So the coordinate of I, j, and k in 3 dimensions is I equals to 1, 0, 0, j 0, 1, 0, and k equals to 0, 0, 1, and in 2 dimensions I just have I and j, no more k here. Awesome. Next remark, we can describe any vector using I and j in R2, using I, j, k in R3. That means we can describe any vector using standard unit vectors. For example, AB, we can rewrite this vector V, whose component AB, as A0 vector plus 0B vector. If I add these two, I'll get the AB vector, right? So then from here, I can pull the A out, then 1, 0, because I need to introduce I and j. From second, I can take a B out, so we have 0, 1, then 1, 0. This is the I vector, and this is the j vector, so AI plus bj. Similarly, in vector in the space for R3, we can write ABC equals to AI plus BJ plus CK. I hope this presentation makes sense to you all. 2 vectors are called equal vectors if they have the same magnitude and directions. Algebraically, 2 vectors are equal if and only if their corresponding component are equal, first to first, second to second. Similarly, in 3 dimensions, first to first, second to second, third to third. Great. Next, 2 main arithmetic operations among vectors is vector addition and scalar multiplications. Scalar multiplications, given a scalar C and a vector V equals to P, Q, then CV scales the vector V. That means if C is positive, then CV and V have the same directions, and magnitude of CV equals to C times magnitude of V. If C is greater than 1, then CV stretches out the vector V, right? If C is between 0 and 1, then CV shrinks the vector V. If C is negative, then CV and V are in opposite directions. If C is constant is 0, then CV equals to 0 vector. Awesome. Let's move on. Algebraically, the scalar multiplications C times the vector V, we can multiply that constant or the scalar component wise. So CP time comma CQ. 2 vectors are parallel if one vector is a scalar multiplications of the other vector. For example, V and CV vectors are parallel vectors, and we write the parallel vectors by these notations: V parallel to CV. Similarly, V parallel to its unit vector. Similarly, V vectors, 2 times V vectors, or 5 third vectors, or -7 times V vectors are all parallel to each other. Awesome. Next, let's talk about vector addition. There are 2 types of vector additions: triangle law and parallelogram law. So let's talk about triangle law. Suppose we have 2 vectors U with component P and Q and vector V with component R and S. triangle law. Draw them tip to tail and connect the tail to tip. So that means, let's say we have u vectors, we have v vectors. So here, fix the v vector as it is, and these vectors are free floating object. So just copy the u vectors and paste here, paste in such a way that the tail of u vector connects or joins the tip of v vectors here. Then join the tail of v to tip of u. Then this vector is the sum of these two vectors. Or we can fix u vectors and we can copy the v vectors and paste here at the putting the tail of v vector at the tip of u vector, and then join the tail of u vector to the tip of v vector. Then this red vector is the sum of the two vectors. So then it forms a triangle, so the name is triangle law. Similarly, parallelogram law, place both tails of the vectors connected to form adjacent sides of a parallelogram. Then the diagonal vector is their sum. Then this diagonal vector is their sum. Great. Now algebraically we do arithmetic operations component wise. U plus v is the u vector, this is the v vector, so we add the corresponding component. Awesome. I hope this vector addition and scalar multiplication makes sense to you all. Now let's move on. Another way of describing a vector is by using the directions. For example, let's say we have a unit vector v, then this v vector is a component, let's say is a pq or cosine theta sine theta, because this is the unit vector, so this length is 1. Then we can write our vector v equals to cosine theta comma sine theta, or using I and j, cosine theta I plus sine theta j. But if our vector lies here, which is let's say outside the unit circle, then this whole magnitude is v. Then this component is the magnitude of v times the cosine theta, and this component is magnitude of v times sine theta we used here. So this is here. So v times cosine theta, magnitude of v times sine theta. In terms of I and j, we write vector v equals to these last expressions. Great. Next, let's talk about properties of vectors. Let's say we have 3 vectors and 2 scalars, then vector additions and scalar multiplications. So first, vector addition is commutative. We can switch the positions and add them, still will get the same vectors. This is true in real number also. If I add 2 plus 5, which is 7, or I can switch the position of 2 and 5 and add 5 and 2, I'll get 7. Similarly, vector addition is associative. I can switch the position here again. So 0 vector is an additive identity. And additive inverse, if I add vectors and is negative of that vectors, it gives me 0 vectors. Scalar multiplications, the scalar is distributive over the sum. The sum of the scalars, I can distribute this vector again. If I have ab times u, then I can only multiply vector u by b and then multiply by a, or multiply u by a and then b. It turns out the same, associative. And one is multiplicative identity. 1 times u is always u. Awesome. Now I hope this theory, these definitions make sense to you all. Now let's do some example. So worked examples. For given vectors u and v in the space, compute the followings. Now a bunch of multiple sub questions. Part A, find their sum. So the solutions, we can add the 2 vectors component wise. So then 8 plus 5 here, 1 minus 2 second component. In the third component we are adding negative 4 plus 1, which turns out to be the vectors 13 with component 13 comma minus 1 comma minus 3. Part B, let's multiply the u vector by the scalar 4, v vector by scalar 2, and then add them. So again, how we multiply the scalar to the vector? Again, component wise. So first multiply this 4 to each of these component of u vectors, which I did here. Then plus multiply the v vectors each component by 2, which I did here. So 2 times 5 is 10, 2 times minus 2 is minus 4, and 2 times 1 is 2. Then add these two vectors again component wise, which gives me this vector whose component is 42 comma 0 comma negative 14. I hope you are following me so far. Now let's do it part C. Let's subtract these two vectors u minus v. Again you subtract component wise. So then 8 minus 5, 1 minus minus 2 means 1 plus 2, minus 4 minus 1. It turns out to be this vector with component 3 comma negative 5. Great. Let's do part D. Let's compute the magnitude of the vectors u minus v. Then by formula, under the radicals, the x component is square plus y component is square plus z component is square, which turns out to be radical 43. Part D, let's compute the magnitude of v. So this vector, again by formula, under the radical, this 5 is square, minus 2 is square, 1 is square, which turns out to be radical 30. Next, part F, let's compute the unit vector of v. So by formula, we divide each of the component of v by its magnitude. So then magnitude is, which computed in E here. So magnitude is 1 over radical 30 and the v vectors here. And if I compute the magnitude of unit vector v, it turns out to be 1. Right. Similarly, part G, find the vector that has the same direction as a v vector but has length 7. I hope this question makes sense to you all. Find the vector that has the same direction as v. So obviously we pick unit vector following the v, and we need the magnitude 7, so multiply the unit vector by 7 times v unit vector. It turns out to be the required vector for part G. Great. Let's move on. Now example 2. Example 2. If the vector v lies in the first quadrant and makes an angle 2 pi over 3 with the positive x-axis, then find the vector v if we know the magnitude of v is 3. Let's see the diagram here. When the angle is 2 pi over 3, then our vector lies in second quadrant, not in the first quadrant, and it makes the angle with the x-axis is 2 pi over 3. Okay. So now this is the second quadrant. So then let's begin the solutions. So our solution is vector v equals to magnitude of v cosine theta comma magnitude of v sine theta. Theta is 2 pi over 3. So we know magnitude of v is 3. Let's put those values here. We know cosine 2 pi over 3 is minus 1/2. Sine 2 pi over 3 is radical 3 over 2. So the required vector is negative 3/2 comma 3 radical 3 over 2. These are the components of this vector v. Awesome. Now let's move on. Example 3. Example 3. Find the vector v in terms of vector I and j represented by the directed line segment joining 2 point A with coordinate 3 comma minus 1 and B with coordinate 2 comma 3. So first let's find the vector. Now we need to find the vector joining these 2 points. So the formula is tip minus the tail. So that means 2 minus 3, 3 minus 1. So first the vector AB equals to 2 minus 3, the first component. Second component is 3 minus 1, so 3 plus 1. So minus 1 comma 4, and then use the angular bracket. And when you are rewriting the vector using I and j, we don't need to write the angular bracket. We write negative 1 times I plus 4 times j. Now the final remark, all the vector results from R2 follows analogously in the space R3 by just adjusting the z component. For example, we can write the vector v in terms of I, j, and k if you have a point here in 3D, that means with 3 components here. Awesome. So we finished this vector introductions in today's class. We'll do more vectors in our next class. Thank you.